Hello and welcome. This is lecture 2 of Organic Chemistry 1. I'm Patrick Willoughby. In this lecture, last lecture, I guess, let's kind of recap. We talked about chemical and physical properties, really just in terms of definitions, and we talked a little bit more about physical properties. Today we're going to talk about chemical properties. Just a reminder, this course is designed for students that maybe haven't had chemistry before. So for those of you that are looking for a more traditional sophomore level experience, that's coming, but for now we're kind of trying to get everybody onto the same page. So without further ado, let's get our notes up in front of us. Okay, so as I said last time, we talked about physical properties. Today though, we're going to talk about chemical properties. So chemical properties. And really what this is looking at is the chemical reactions that our matter is capable of. So whatever we're studying, whether that's some trivial organic compound, organic molecule, or a more complicated molecule, like a biological entity like a protein or something, whatever it is, whatever that chemical is or that form of matter is, the chemical properties are what we call the chemical reactions that thing can undergo. So as you're thinking about the definition of chemical properties, you really want to focus on the term chemical reactions. Okay, so let's think about an example of this. The combustion of methane. Combustion is a great reaction to start with, a great chemical property of a system to look at first. And that's because it's fairly repetitive, and it's super important as we kind of think about energy and really climate in the future. Okay, so the combustion of methane. So methane is probably a newer term to most of us. So methane is a chemical. Really, it's a molecule. I won't worry too much about having you worry about the differences between the words chemical, molecule, and compound. There are important differences, but not something we need to worry about right now. So methane is a molecule with the formula CH and then 4. Notice the 4 is drawn as a subscript. That is, it's little and it's lower to the right of the H in this case. So what we have here is we have a formula. Let's define, in case we haven't seen this before, no big deal, we'll define the term molecular formula. Molecular formula is just simply a list of the type and number of elements in our matter that we're studying. So I know the word matter is kind of weird here. You maybe want me to say molecule, compound, chemical. All of those are fine and probably better. But I'm trying to avoid us having to worry about kind of knowing the definition of those terms, as I mentioned just a minute ago. So it's a list of the type and number of elements. So elements come back to our periodic table. And in upcoming lectures, we'll talk about the periodic table that we'll actually use in this class that I would recommend using as you solve problems and work on tests and that sort of thing. But I mean, periodic tables are everywhere. Google search them, you'll find so many images. So what CH4 is showing us, what CH4 is showing us is that we have two types of elements. C, which is carbon, and H, which is hydrogen. So these two elements make up methane. Further, we have the number 4 listed next to the hydrogen. And because it's subscripted, or lower right of that hydrogen, we say that that is the number, number of hydrogen atoms. The number of hydrogen atoms. Okay, I'm going to skip to the next page. Feel free to pause. Okay, I introduced a new term, and that was atoms. We're going to be talking a lot about atoms in upcoming lectures, but for now, we'll say these are the individual elements within our, I'm just going to go ahead and start using the word molecules because that's mostly what we're going to be looking at. So atoms are the individual elements within our molecules, could be compounds, any type of matter. Okay, so atoms. Atoms have, these are the things that have, they're made up of many subatomic particles, it turns out. I'm going to simplify things a bit just to keep the discussion going. So they're made up of protons, neutrons, and electrons. Okay, so protons, neutrons, and electrons make up atoms. Atoms are the individual elements that make up our molecules. So really, I could be using atoms and elements interchangeably. I'm going to try to be careful and use elements more often, at least in the early part of the semester. Okay, so we said that we had, in CH4, we've got 4 hydrogen atoms. And there's no number here beside carbon, lower right of carbon. There's no number subscripted carbon. Make note of that. Now what that implies to us is that we have a number that's not super significant to write so often, and that's the number 1. That implies that we have 1 carbon atom. Whenever we have 1 of an element, we decide our formula is a little bit simpler if we don't specify that number 1, we just write the C. I mean, if there's C, there's got to be at least 1. If it was C0, we just wouldn't write the letter C. So no number means 1 carbon atom. So CH4 has 1 carbon atom and 4 hydrogen elements. CH4, or methane, is made up of 5 elements total, 4 of which are hydrogen, 1 of which is carbon. Okay, so hopefully that's somewhat clear, but that's where these formula come from. We're going to see the formula quite a bit. So CH4 is a specific type of formula. So CH4 is the molecular formula of methane. So we said methane, this name with English letters and makes an English sound, I guess. That is the name of this compound, but its formula, that is the listing of the number and types of each of the elements, is CH4. So kind of differentiating those two things will be very helpful. CH4 is the molecular formula. Now let's highlight that. That's a new term. A molecular formula is the listing of all elements in our matter, let's say. Okay, whatever matter we're studying. So CH4 is a listing of all of the elements. Why did I have to, and really this is going to focus on molecules. Why did I have to add this extra term in front of the word molecular? Why is that important? Well, there's another term, and that's called the empirical formula. Now, the empirical formula, I'm going to give a pretty standard definition of it, but then I'm going to tell you what it actually means to us studying molecules in the classroom. So the empirical formula would be the formula. So with formula, I mean listing and number of each, listing of the types and the number of each of those elements that make up the matter of interest that we're studying. So empirical formula is the formula that we would obtain by many experimental techniques. So experimental kind of goes with the term empirical. So if we actually went in a lab and we had some methane, like it said methane on the bottle, but we didn't know what its formula was, and we tried to measure it, we would obtain the empirical formula. So it's the formula that we would obtain by experimental means or empirical means, okay? But what this means to us is there's a bit of a different definition, and that is the empirical formula is the molecular formula divided by a common denominator. Uh-oh, I'm going to run out of space. Apologies. Denominator. Denominate. Goodness. Let's just clean this up. There, a common divisor. Let's change page and we'll cover this again. So empirical formula, what I'm trying to say is the empirical formula is the molecular formula divided by a common denominator of our subscripts. Okay. Let's look at an example of this. Okay, glucose. Glucose is a good example. So glucose is a molecule that we often call sugar, saccharide, carbohydrate. It's a pretty standard type of each of those. It's pretty standard sugar, carbohydrate, saccharide. It's readily abundant everywhere. Table sugar is glucose. You'll see it everywhere in biology. Anyway, so glucose. That's a little backstory of it, but let's talk about its formula. So the molecular formula is C6H12O6. C6H12O6. Now, what I want you to notice is that the subscripts are all divisible. That is 6, 12, and 6 are all divisible by 6. Okay, so what we could do is instead of writing this C6H12O6, we could take the molecular formula divided by 6. Where did the 6 come from? It's a common denominator. And that's going to give us our empirical formula, which is going to be CH2O. CH2O. Okay, so what I'm saying is that glucose, truly, if you take a glucose molecule, it has 6 carbons, 12 hydrogens, 6 oxygens. C6H12O6. In case you didn't know, O was oxygen. But if we went in the lab and we tried to measure what its formula was, under many standard analytical techniques, we would get a formula of CH2O. The correct ratio of the elements would be intact, but the absolute number of each of those elements would be incorrect. So within empirical formula, the ratio of elements is correct. So the ratio of elements in an empirical formula is correct. but the absolute number is wrong. Okay, the ratio is correct, the absolute number is wrong. Now, you might be like, well, if it's wrong, why is it useful? Remember, standard analytical techniques, this is what we had useful or available to us for a long time, us as chemists, that is. We got better. Certainly, there are instruments that we can just inject samples on, and they will tell us exactly what the structural formula is. It's quite impressive, but for a while, we didn't have that. Now, you might notice some issues with this. The empirical formula doesn't seem all that useful because it's not correct. Maybe we get some hints of the structure, but here's an issue. There's an issue with this, and that's coincidental matches. That is to say, if I look at the, if I have a molecule and I look at its molecular formula and I look at its empirical formula, there could be some coincidental matches for many molecules. So, for example, we have glucose. Its molecular formula is C6H12O6. Its empirical formula, we just said, was CH2O. Okay, there's another molecule out there called formaldehyde. Formaldehyde is highly toxic. It's classically used as a preservative agent, but then we realized how dangerous it was maybe to even be exposed to small amounts of it, so we've replaced it with other things. But it preserves tissue, that sort of thing. Nothing can really grow in it. So if you don't have bacteria growing in some dead tissue, it can't be digested and it's preserved. Okay, so formaldehyde has a molecular formula of CH2O. Now maybe you want to pause for a second and think, what's the empirical formula of formaldehyde? So remember, the empirical formula, we're going to take each of the subscripts below the numbers and divide them by some common denominator, some common divisor, so we only get whole numbers. If you look in this case, we've actually got 1 subscripts that we have to, we just don't write. Remember, if the letter's there and there's no number, that implies there's only one of those elements. So in formaldehyde, there's indeed only 1 carbon and 1 oxygen along with the 2 hydrogens. If you've got the number 1, you can't divide it by all of the subscripts by a number greater than 1. So dividing C1H2O1 divided by 1 in every case just gets you CH2O. So there's an issue. Glucose, which is a very important molecule for biology and sustaining life, has the exact same empirical formula as formaldehyde. So there's shortcomings if you just measure the empirical formula, because you want to make sure you know the difference between formaldehyde and glucose. Now, obviously, there are other things, like table sugar is a nice crystalline white solid, whereas formaldehyde is a foul-smelling liquid. Okay, now actually it's more, and that's in aqueous solution actually polymerizes to a less crystalline solid than table sugar. Anyway, details. Okay, so what we notice here is that in the case of formaldehyde, the empirical formula and the molecular formula are the same. So I just want to come back to methane, which was CH4, and ask the question, what is the empirical formula of methane, which again we said was CH4. Okay, just giving you a second. You can always pause. All right, so CH4, once again, just like with formaldehyde, we've got a 1 subscript and we can't really divide any more than that. So CH4 stays as CH4. Okay, you know, there are other examples of situations like this where the empirical formula and the molecular formula are the same. It's actually quite helpful when that's the case in terms of classical analytical techniques. Honestly, though, we can move on to more sophisticated analysis and really get a good idea of what the actual molecular formula is. Okay, so we're going to move on now to a new topic, and this is going to be combustion reactions. Okay, so combustion reactions are, in combustion reactions, this is a chemical process where oxygen is ignited with some sort of fuel source, okay, a hydrogen fuel source to generate water and energy, and often, in our case, the byproduct carbon dioxide. So in combustion reactions, O2, which is oxygen as you find it in nature, or what we call molecular oxygen, is ignited in the presence of a fuel source. And this is a special fuel source. This is a hydrogen donating fuel source. So a hydrogen source. And the product is always water plus energy, and sometimes, for us, mostly all the time, CO2 or carbon dioxide. So we get water and energy out, sometimes CO2, which is carbon dioxide, whenever we take oxygen and ignite it in the presence of a hydrogen fuel source. This is a broad class of reactions called combustion reactions. Now, what we can do is we can actually draw a chemical reaction equation to describe a combustion process. So a combustion chemical reaction equation. Okay, so what we do here, it's actually, in my opinion, compared to all of the equations I've studied, as you know, when I was in your shoes being a student, this is kind of the least formal in a lot of ways. There's no equal signs. Instead, there's just some arrow indicating the direction that a process can go. And sometimes, as you know, there are a couple arrows. So what I'm saying here is we're going to take O2, which again is oxygen. And this is oxygen that we encounter in nature for the most part. So we call it molecular oxygen. Just having a single oxygen atom or a single oxygen element is difficult to do, to hold on to very long, because it's unstable. It's more stable as the diatomic molecule in this case. What we're going to do is add that to a hydrogen fuel source. And so let's start with hydrogen itself, H2. So this is just like O2 was molecular oxygen, H2 is molecular hydrogen. It has two hydrogen elements. And we're going to mix those two together. And we are going to provide some sort of ignition source. One way of describing an ignition source is to put a triangle. The triangle has a really broad, it's a symbol that's used quite a bit, especially in chemistry. The triangle is considered the capital D in the Greek alphabet, or capital delta. And what it really refers to is change. So what this is saying is change. Now, when we put a triangle over an arrow, this tells us that we are going to mix two things together. In this case, oxygen and hydrogen. And then the triangle says we're going to change the energy of the system. Generally, whenever we have the triangle, we increase the energy of the system, usually by providing some sort of heat. So you could imagine having oxygen and hydrogen and igniting the combustion reaction between the two, how you would ignite any combustion reaction that you've done before. And that's just like with a match or something. You've probably done this maybe in some science class. It makes a really wild pop. It's kind of fun. And the outcome of this is you're going to form H2O in this case plus energy. Now, I want to just have an aside. It turns out the triangle symbol was actually shorthand for flame back in the day. So a long time ago, the delta, the term delta, and the triangle symbol that we've used in several branches of science for years is actually supposed to be a small flame. Anyway, that aside, that was just kind of something to keep in mind, I guess, as to where this comes from. So just to reiterate that, this delta here is heat/ignition, and it's a symbol for it. We're going to use it a lot. You'll see it a lot whenever you study some sort of chemical process. Okay, so this is a partially formulated chemical reaction equation, okay? The attributes are, we're going to have plus signs. We have some plus signs here and here, and those indicate when we're adding things together or getting a mixture of things. So we added oxygen and hydrogen as a mixture. We get out at the end of the day a mixture of water plus some energy. Okay, I'll get rid of those highlights there. We have this reaction arrow. The reaction arrow is in chemistry is kind of like the equal sign in traditional mathematics. So this is kind of connecting two processes, a left side and a right side, I guess is sometimes called a starting material and a product side, if you want to do it that way. It's just one set of types of matter, chemicals, molecules, whatever, compounds. One set of matter is interacting to form a new set of matter, and usually there's an energy component on one or two of the sides of the chemical reaction equation. So the arrow is really our equal sign. And then above the arrow, we put certain things that aren't considered reactants. They may not be involved in what's called the stoichiometry. That's a nuance that we'll get to later. But for example, the ignition source wouldn't be involved in what we call the stoichiometry, or how many of each element that we have. It's just kind of something we need to do the process, but it's not necessarily contributing to the number of oxygen elements that we have. And as a result, we put it above the arrow. And there will be many things that we see that just kind of go above the arrow. Okay, getting rid of our arrow. So we have a chemical reaction equation. Now, I said this was a little bit half-baked, not quite there. And the reason why is we can't forget about one of the most important physical principles of all, and that's the conservation of matter and energy. The conservation of matter and energy. And there's so many ways to define this, all of which are useful. Remembering that you all will probably take some physics. I'll just be a little bit shorter in our definition. And I will basically say that because of the law of conservation of mass, matter, and energy, sometimes this is mass instead of matter, because you cannot, because this law, what this law says is that you cannot create or destroy matter / energy. Instead, what you can do is you can only, I'm just gonna put a period here, you can only transfer matter / energy to different states. Now, and it helps if we keep this kind of simple, if we focus on some of the processes that are practical for us, right, on planet Earth, for example. So one example that might be less practical is worrying so much about annihilating matter and antimatter and that sort of thing. Let's just think instead about when we're looking at the matter or the mass of a system, let's just think about we can't destroy elements. Okay, we can't destroy elements. Let's stick to that. That'll help us get started in what we call balancing chemical equations. So recall I called this the mixture of oxygen and hydrogen, and then using the arrow to get to water and energy. I called that an equation. There's no equal sign and that sort of thing. What's underlying our chemical reaction equation is the law of conservation of mass or matter and energy. Okay, using that and knowing that exists as a law, a physical law, this becomes an equation because the number of elements on one side must equal the number of elements on another side. Okay, so we've got a left side and we've got a right side. The number of elements on either side must be equal. So if we look at this though, let's draw this again. O2 plus H2 equals H2O plus energy. Now, if we look at the elements on the left side, we've got 2 times oxygen plus 2 times hydrogen. And this goes to 2 H's and 1 O. That looks like a 10. Put a 1 times O. Okay. Well, according to the conservation of matter and energy, we can't start with 2 oxygens and end with 1 oxygen. Okay, that's an issue. So we've destroyed matter if we lose an oxygen. So we put 1 oxygen in, we put 2 oxygens in, we don't get 2 out. That's an issue. That violates the conservation of matter and energy. Okay, so what's happening here? What's happening is more of a technicality. We've just written our equation wrong. We need to balance our equation. Okay, so very important skill. We need to balance our equation. And by balance, I mean we need to add molecular coefficients to our reactants and products. So the reactants and products, these are our forms of matter, our molecules, or our chemicals on the left and right side of the equation. Okay, so what does this look like? What we're going to do is we're going to add numbers to the front of our compounds, our forms of matter, to make sure that the number of elements balance. Okay, so what that looks like in a final stage is we're going to take O2 plus, instead of just writing H2, we're going to write 2H2 and let that go to, instead of H2O, we're going to go to 2 H2Os. I'm going to put a triangle for my ignition source, or a delta, as I should more correctly say. Now what this does is we're going to use this 2 to say for each of these reactions, we're going to have to use not 2 hydrogen elements, we're going to have to use 4 hydrogen elements. Because if we have 4 hydrogen elements over on one side, 4 times H, and we let that add to 2 times O, the product of our reaction will be 2 water molecules, or something that has, if you look, 2 H2s, that's going to be 4 times H on the right side, plus 2 times O on the right side. So now if you look, this is consistent, or it does not violate our conservation law. Okay, so all the matter that we started with, we ended with, which is great. We start with 2 O's, we end with 2 O's. Now what that required was increasing the amount of hydrogen that we put into the system, and then also increasing the amount of water that we got out of the system. Okay, now why don't we just do this? Why don't we just do O2 plus H4, okay? Wouldn't that do the exact same thing? That would show putting a 4 as a subscript to H, 4 hydrogens go in. Well, it turns out that H4 is not a stable molecule. You can't go to the store or go to the Aldrich, which is sort of the Amazon of chemistry. You can't buy or put H4 into a bottle very easily. Instead, what you want to do is get a cylinder or some container of H2 gas. So we can get our hands on H2 and we can get really as much as we need, okay? So if we can get as much as we need, it's way easier to grab a little bit more H2, maybe 2 molecules of H2 for each of these reactions that proceed. It's just easier to add more H2 to the system. Similarly, if I thought to myself, well, what if we just made instead H4O2 as a product? Okay, that's another way of asking this question. Why do we put the numbers in front if there's numbers in front and down and to the right? Why do we need the numbers in both spots? Well, H4O2 is also not a stable molecule. So I'm going to put a question here, and this molecule is also not stable. Not stable, we can't put it into a bottle. It's way easier to think, instead of trying to make unstable molecules that the universe doesn't like to put its hand on, instead of doing that, let's just make more water, okay? So we have, instead of our original equation, we make twice as much water when we add twice as much hydrogen with the same amount of oxygen. So the coefficient goes in front of the molecule to tell us how many of each type of these molecules we're going to use, and the subscript down and to the right of each element tells us how many of each type of element make up that molecule. So let's kind of recap. Subscripts show how many elements, or the number of elements, and coefficients. And maybe what I'll do is I'll put 2 O2s in this case. So the coefficients show the number of molecules or compounds or whatever form of matter you have. Maybe it's a salt. Always works. So coefficients are the yellow, and subscripts are the blue. Okay, so knowing the difference between those is critically important to really understanding chemical equations as we go forward. Okay, so let's do some more combustion reactions. Now, why would you want to do combustion reactions? It's one of the most popular reactions, and that's because it generates a ton of energy. I haven't really talked about the energy part of the equation, but we'll get there. We can talk about it just briefly right now. So I'm going to take CH4 in this case, and I'm going to put a header on this. Let's call this the combustion of methane. Sorry, that's getting into my O2 a little bit there. There we go. Okay. So we have the combustion of methane. We're going to take CH4, which we saw was methane, the both molecular and empirical formula of methane. We're going to add that to O2 with some sort of ignition source. Okay. And we're going to form, in this case, H2O plus, I'm going to leave a space here, something plus energy. You always form energy when you do these processes. Now, you might think, well, there's energy on the right. Why isn't there energy on the left side of our chemical equation? That energy is actually buried into the starting molecules. The O2 and the hydrogen fuel source have energy buried into it that's potentially could be unleashed. And that word potential is important. It could be unleashed and used for movement energy and that sort of thing. That's why you put gas in your car. We do combustion reaction on the gas. The gas has stored in that liquid chemical a lot of energy that we can use to move cars. Okay, so I said that we want to leave a little space in this combustion chemical reaction equation, the combustion of methane, and that's because we have a new molecule that's being generated. If you notice, if we have a carbon in CH4, a carbon in one of our starting materials, we need to have a carbon in one of our products. And in this case, we're going to form carbon dioxide, or CO2, as our product. So this is carbon dioxide. Now, balancing these types of equations has another sort of wrinkle in it. So what we want to do is we want to balance combustion reactions with carbon. Okay, I have a few rules. If you've seen this before, if you've learned this before, use your rules, whatever's helpful for you. I'm just giving you something that you can use to be helpful. My general thought is you should always start with carbon. So if we need to balance a combustion reaction with some carbon hydrogen fuel source, I say we start with the carbons. Step 2, we then balance, and what I mean by that, that's kind of a weird phrase, start with carbon. I'm going to rewrite that and say balance the number of carbons. And I'm going to do the same thing for number 2. I'm going to say balance the number of, but in this case, I'm going to move to hydrogen. Now, what I've noticed is that students do better if they leave oxygen for last. And that's because with oxygen, there's actually 2 sources of oxygen, in the hydrogen side and in the carbon side. There's generally fewer carbons, so I'd say start with the carbons before you move on to the hydrogens. So third step is balance the number of oxygen atoms. Okay, so we've got our 3 types of elements, and I'd recommend going in this order, okay? So let's apply that to our combustion of methane. So we have CH4 plus O2, and we want to add H2O plus CO2. Okay, I'm going to put a little space here. The goal of balancing chemical reaction equations is to introduce the proper coefficients so that the number of each type of element is balanced. Okay, so for carbon, we have 2 sources of carbon. We've got CH4 and CO2. Those are our 2 sources of carbon. If you look, we've got 1 carbon element on the left, and we've got 1 carbon element on the right. 1 times C on the left, 1 times C on the right. Those are already balanced. So in step 1, when we're balancing the number of carbons, it seems like, well, all we need to do is add a 1 coefficient to both sides. Now let's move into the next element. In this case, that's hydrogen. So we have 4 times H on the left, no hydrogen contribution from oxygen, and we have 2 hydrogens coming from our water molecule. Okay, so we want to add a coefficient somewhere to get these to balance. Currently, they're not balanced. We have 4 hydrogens from CH4, 2 hydrogens from water. What I'd say is we introduce the coefficient 2 in front of our water. That would mean we have 2 water molecules being produced, which allows us to form 4 hydrogens on the right side to balance the 4 hydrogens that we put in on the left side. Note that unlike before, well, I guess, let's not mention it. Okay, so 4 hydrogens on the left, 4 hydrogens on the right, 1 carbon on the left, 1 carbon on the right. Now let's balance the oxygens. So let's go to the next page here. Okay, so what I'm going to do is just recap what I just had. So CH4 plus blank O2 delta over a reaction arrow, and we said 2H2O plus 1 CO2. Okay, now let's worry about our oxygens. We've got 2 oxygens on the left, and we've got 4 times O from, oh, excuse me, I mean, it's correct, total, but let's break it down. So we've got 2 times O from our water and 2 times O from our CO2. If you notice, our water molecule, while it started with 1 oxygen, now we have to take into account that coefficient that we introduced to balance our hydrogen atoms. So we have 2 oxygens, and we have 2 plus 2 oxygens. That's going to be 4 times oxygen total. So we have an imbalance of oxygen. Okay, so what we could do is we could just double the number of oxygen molecules that we put into the system by adding a 2 at this position. And I'll make that red just so it looks like it's new, so 2. So what this means is that our balanced equation is now CH4 plus 2 O2s delta to 2 H2Os plus CO2. Okay, so that's a balanced chemical reaction equation. The energy is something I like to write, but you don't have to write it. It's something I like to write to remind myself why people are doing this in general, and we'll need to worry more about the energy later. Now, what happened to the ones? Well, we don't write number 1 as both a subscript and a coefficient. So as a subscript and a coefficient. Okay, so and another thing I like to always emphasize to people is this is just one of those problems. We're going to have to solve it on tests. Just check your work, okay? Go back and look through after you've added the last of your coefficients. Make sure all of the elements are still balanced. Even if they're balanced in step 1, we may run into some issues later on. So, for example, if we look at the most important combustion reaction in our economy right now, in our energy economy, in our automobile economy, let's say it that way, because really the combustion of glucose is what gets biology to go, and combustion of many biological molecules. Another day. Okay, so combustion reaction of octane. So octane is the stuff that we put in our car. Okay, it turns out that we can actually get a sense of what the molecular formula is of octane from its name. It was named octane for a reason. It has 8 carbons. So it's C8H18. And we're going to do a combustion reaction. So for all combustion reactions, we have our hydrogen fuel source added to oxygen. We have our chemical reaction arrow, along with a delta to imply we're going to ignite this mixture of octane and oxygen to form CO2 plus H2O. Okay, so let's go ahead and balance this now. So I said let's start with carbons. I'm going to add some blanks here. So we start with carbons. In octane, we have 8 times carbon from our carbon hydrogen fuel source, and we have 1 times carbon from our carbon dioxide product. So before we had methane, which just had 1 carbon in the starting material, 1 carbon in the product. Now we're going to create a whole bunch of carbon dioxide byproducts. In fact, 8 molecules of carbon dioxide will be generated for each molecule of octane that's burned in this combustion process. So I'm going to put an 8 at our CO2 and a 1 at our C8H18, which I should label as octane. I know I use my words, but let's connect it with arrows. Okay, so we've balanced our carbons. I think that's always the best place to start. Now we're going to move to the hydrogens because that's only shows up in one place on the left and the right side of the equation. So using this 1 subscript, we have 18 times H from octane. No contribution of hydrogen comes from oxygen. We go over to the right side of the equation. Carbon dioxide I wrote first. It doesn't matter which one you write first. I chose carbon dioxide this time. It has no hydrogen, so it's not making a contribution to balancing that. But we only have 2 hydrogens from our water. Okay, just like introducing a coefficient would hammer the or would increase the number of carbon atoms on the right side from 1 to 8, we could increase a coefficient in front of our water molecule we could add a coefficient in front of water to increase the number of hydrogens, in this case from 2 to 18. The number that would do that is 9. Because if we had 9 water molecules, each individual water molecule having 2 hydrogens, that would take us from 2 hydrogens at the start up to 18, because 2 times 9 is 18. Okay, so our hydrogen atoms are balanced. Okay, what should we do about oxygen? So with oxygen, Now we have 2 oxygens on the, from oxygen on the left side of the equation. We have 16 times oxygen from our carbon dioxide, and that's because we introduced the 8 coefficient first. And we have 9 times O from our water molecule, because again, we introduced that 9 coefficient to make sure that we had enough hydrogens. So 16 plus 9 is equal to 25. So we have 25 oxygen atoms on the right. How about on the left? We only have 2. Okay, so what we should do is add a coefficient to increase from 2 up to 25. Okay, 25 is an odd number, so if we wanted to add a coefficient that would evenly get us from 2 to 25, we would have to add the number 12.5. That's not a whole number. Now that poses an issue. So I'm just going to give you a second to recognize that 2 times 12.5 is equal to 25. We have a balanced number of oxygens, but we've done something incorrect. We cannot have half coefficients. The molecular coefficients must, important, must be whole numbers. Okay, the reason why is because we can't go into the lab and pull out 12.5 molecules of oxygen. If you're familiar with a term called the mole, then yeah, I guess we could do that. But that's not what I'm saying here. In this balanced chemical reaction, we're looking at individual molecules. How many individual molecules do we need for each singular chemical reaction? I can't give you 12.5 molecules of O2, okay? That needs to be a whole number. We can't split the O2 in half and expect to get the same chemical reaction outcome. We have to keep the O2 intact. So what we do is, if needed, multiply all coefficients by 2 or 3. I've never seen the numbers get higher than that, and for me, you probably won't have to multiply more than 2. But we're going to multiply all the coefficients by 2. So we had 1 C8H18 reacting with 12.5 O2s to give, after some sort of ignition source is introduced, 8 CO2s plus 9 O2s. We're going to multiply by 2 across the board because we recognize that an issue is we can't have 12.5 oxygens. We need a whole number of oxygens. So multiplying by 2 across the board gives us 2 octanes plus, now 2 times 12.5 is 25 O2s. With our ignition source, we're going to get 16 CO2s. Just make that nicer, plus 18 O2s. Okay. So that's now a balanced chemical equation. And I believe that's a great place to stop. Okay. So today we talked about formula. We looked at, we started by just talking about chemical properties in general. Then we finished by looking at balanced chemical reaction equations, describing a really important chemical process, which is the combustion of octane, something we do every time we start up our car and for an extended period of time. Hopefully those of you that are kind of worried about the carbon dioxide levels, which probably is most of us at this point, recognize that octane's nice because it's a nice energy source, but it provides a lot of carbon dioxide every time that we do a single combustion reaction of it. Okay, so those are hopefully some of the insights that we can glean. Something I just want to keep reminding everybody of is it's still early in the game. So if you're watching this and you're like, you know, I know how to balance these reactions, I learned that in high school AP, just remember that's not the case for everybody. And, you know, fortunately with this lecture format, you can always feel free to skip ahead or make me talk fast and write faster. by kind of increasing the playback speed. Okay, hopefully you enjoyed that, and I'll see you next time.